So today we are very happy to have Katerina Chatziioannou visiting us. She is an assistant professor of physics and a William Hurt scholar at Caltech. She did her PhD at Montana State University, and then she was a postdoctoral fellow at CETA, and then a Flatiron Research Fellow at CCA. She works on a wide variety of things related to gravitational waves, data analysis beyond GR, and neutron stars. And today she'll talk about studying neutron stars and dense matter with gravitational waves.
Okay, good morning. Thank you. Thanks for being here. It's a pleasure to be here. Very nice location after coming from New York earlier this week. Okay, so my research is broadly revolving around gravitational waves and how we can use them to study various things. I checked your recent calendar. You've had lots of talks about gravitational waves recently, and you have a local gravitational waves group. So I assume you kind of are familiar with some of the typically introductory material, what gravitational waves are, why we're interested, what we can do. So I am going to mostly go into, directly go into the topic I would like to discuss today. But if you'd like a little bit more discussion, background questions about LIGO, etc., let me know. So gravitational wave astrophysics started, of course, a few years ago, and since then progress has been quite rapid. Now there is dozens of detections of black holes and neutron stars with gravitational waves. And if you want to count the nanograph ones, there's probably literally thousands, but let's only count the LIGO ones so far. And this kind of schematic shows the black holes, a subset of the black holes and neutron stars observed either with gravitational waves or electromagnetically. So the y-axis here is the mass in solar masses. The black holes are up here. The gravitational wave black holes are in black. They are in binaries. We see two of these objects coming together, merging, giving a final object. And the neutron stars are down here, around 1 to 3 solar mass or so. So there's a quite big divide between black holes and neutron stars. There's a lot of things going on in this low mass region that we don't fully understand, but there's some things we understand. We know that there should be a very sharp divide between black holes and neutron stars. This has to do with how fast the speed of sound can be inside in nuclear matter. So if you don't want it to exceed the speed of light, you have a limit of about 3.2 solar masses. This could be plus minus a little bit, but there should be a hard limit above which you can't have neutron stars. You need to have black holes. There seems to be maybe a little bit of an observational gap between black holes and neutron stars. What actually happens in this region between, say, 2 solar masses, 5 solar masses is quite uncertain. And I'll get back to this and discuss what gravitational waves can do about this and how it affects our understanding of what we're observing. But within this context, what I'll be talking about in this talk are these objects here. The neutron stars and some question marks, and I'll explain why we have question marks there, that are detected with gravitational waves. So the orange objects on this diagram. So the protagonists are today is neutron stars, and neutron stars are quite remarkable objects. They're the most extreme matter object that we know of. Anything more dense than a neutron star is doomed to collapse into a black hole. And it reaches the level of compactness necessary so that we can see them with a detector like LIGO. This is the only material object that you can see with LIGO. Anything less compact, like a white dwarf, is too big. We cannot detect it with ground-based gravitational wave detectors, but we can do neutron stars because they are small enough. And they are so small, so matter inside neutron stars is compacted to such extreme densities that you end up even exceeding the nuclear density, the nuclear saturation density. So in this nice schematic that kind of cuts through the neutron star to show you the different layers, if you go all the way to the center of neutron stars here at the core, even the kind of the properties and the composition, the nature of matter is unknown. As you pack neutrons and protons closer and closer together, it's unclear whether you end up having phase transitions and liquefying quarks or any kind of other exotic particles. So these are sort of the big questions that interest people about neutron stars. Is essentially, what are the properties of matter inside of them, and what are the observational imprints of this matter? So because of this large uncertainty, nuclear physicists have spent essentially decades trying to calculate theoretically what the properties of matter are inside neutron stars. This is called the equation of state. For the neutron stars that we are interested in, you can do a very good approximation, ignore the temperature, assume they are extremely cold. So the equation of state is essentially a relation between the pressure and the density inside the neutron stars. So the equation of state, so that would be these lines are theoretical calculations from nuclear physicists for the equation of state of dense matter, dense cold matter in beta equilibrium. The astonishing thing about neutron stars, and where astrophysics and gravitational waves eventually come in, is that each of these nuclear physics lines on the left plot for the pressure as a function of density is in a one-to-one correspondence with a line on the right for the mass and the radius. So that would be the mass and the radius of a big macroscopic object, the neutron star. So nuclear physics comes in here, astrophysics comes in here by studying neutron stars. And because we have a one-to-one correspondence between the left and the right, you can actually translate our observations back to nuclear physics, or translate nuclear physics calculations to what you expect to see observationally.
Can you remind us what's the rho stat?
Here, this is a saturation density. It's about 10 to the 14 grams per centimeter cubed.
Saturation of
Nuclear saturation density.
nuclear saturation.
And this is hit somewhere close to the outside layers of neutron stars. And as you go to the center, you go maybe up to 4, 5, 6 times saturation density.
When you say 18 orders of magnitude, what plot?
Yeah. So this sort of nuclear physics, astrophysics correspondence basically takes you down to densities, the level of femtometers. And this physics, the physics of what happens down to femtometers relates to the observational appearance of kilometer-sized objects. So those are the 18 orders of magnitude I'm talking about, from down to the femtometer, and the properties of, say, deconfined quarks at the cores of neutron stars, to the kilometer-sized objects we're seeing in astrophysics. I think there was another.
Why is there such a sharp jump in the mass over radius curve?
Oh, here?
Yeah, like this steep. Slope.
Yeah. So what happens is essentially those stars. So as you go to the center star, you integrate from here out to here, and the pressure support in this case is provided by neutron degeneracy mostly in these layers, and the result is a curve like this. So you don't have a sort of an object like the Earth where you add more mass, it basically adds more layers. Right, if you increase the mass, you increase the radius. Because of the degeneracy pressure, as you add more mass, the radius could go down or stay constant, in some cases increase a little bit. It has to do from the fact that the kind of pressure that supports those objects.
I might add to that if I could. There's a nuclear repulsion force, and so the effective gamma is 2 plus. And under those circumstances, the effective polytropic index would be 1. And for a polytropic index 1, you get constant radius. Then there are GR corrections to this. And it's not exactly a constant gamma, but that's why you get something like a constant radius, which is similar to what you get for Jupiter planets. They also have a similar polytropic index, but without the gravitational, the GR corrections.
Thank you. Okay. So, right. So the other thing to see here, nuclear physicists have all these calculations, which result in basically predictions for neutron stars between 10, 15 kilometers. I'm going to show you that we've actually constrained this a little bit more in a second. But this is a large uncertainty. We have a 50% uncertainty on the sizes of these stars. In astrophysics, a 50% uncertainty on a size might not sound big, but it's actually something that we can leverage. And because of this variation, if you measure properties, macroscopic properties of neutron stars say something about the nuclear physics. Okay, now enter gravitational waves. What happens when you have two neutron stars interacting and giving off gravitational waves? So you might mostly be familiar with gravitational waves from black hole binaries. They look kind of like this. So this is the first one up there, 5914, and a few more down here, and you'll see this characteristic, well, obviously oscillations, because it's a wave, but this amplitude increase, this frequency increase, this is what a typical signal from two black holes merging looks like. And it lasts for, well, milliseconds, maybe seconds. It's a short signal. It's a transient short signal. Compared to that, the signal from a neutron star binary, this is here 170817, looks kind of like this. It'll go on for a while. We actually observed for about 2 minutes. I'm not going to play this for 2 minutes because it will be boring. But the first thing you know is that this signal lasts much longer, it lasts for minutes. So the moment you see a signal lasting for a long time, you know that you're dealing with low mass objects, no longer black holes, potentially neutron stars. The second thing that differentiates neutron stars and black holes is when they actually merge, because black holes are small, and well, neutron stars are small, but still they're about 10 kilometers big. So when they get to their very late stages, they violently collide because they're made of matter rather than just vacuum like black holes. They violently collide. Here's a simulation of two neutron stars doing this. Matter is ejected all over the place. The gravitational wave signal is a bit of a mess. So these very late stages also are very different between when you have a binary of black holes versus a binary of neutron stars. Okay, so let's focus a little bit more on the signal to understand how it's different and how we can leverage this. The plot here shows you signals in the frequency domain. So this is as a function of frequency. So you see the typical frequencies in which LIGO operates, the audible band. And the y-axis is basically an estimate of the amplitude. The amplitude spectral density in the frequency domain. The U-shaped lines are the detector sensitivity. So the lower down those lines are, the better. Blue is the sensitivity at the time when the first neutron star binary was detected. Gray is the design sensitivity, or at least some estimate of the design sensitivity. And the lines going down, mostly the yellow one, are what the gravitational wave signal for two neutron stars colliding looks like. So the different colors are different equations of state. So different nuclear properties, different properties for the matter inside neutron stars, just to get an estimate for how the signal changes when you change the nuclear properties of neutron stars. So early on, there isn't much different. All the lines are on top of each other. This is what we call the in-spiral, the stage where the neutron stars orbit around each other for a very long time. This lasts basically the entire time we're observing the signal. When I say we see this for 2 minutes, we see it for 2 minutes in this stage. At the very late stages, lasting for milliseconds, the neutron stars get close together and they start interacting with each other. And the matter properties start having an imprint on the gravitational wave signal because you can tell apart the different colors. Eventually, there's no turning back. The neutron stars will collide. Typically what happens, but not always, they will fuse together in one remnant object and they will keep violently rotating and emitting gravitational waves that can again carry an imprint of the properties of matter. So what I would like to do is go a little bit more detail in each of the three stages and discuss what we can learn from them and what we actually learned when we observed signals. Okay, let's start with the in-spiral. This is what gravitational wave signal looks like from two in-spiraling neutron stars looks like. It's impossible to really make sense of it. We typically don't plot it because there's so many cycles. It just looks like a solid thing. But if you zoom in here, there are tons and tons of cycles. So the neutron stars, if you start observing them when the gravitational wave frequency is 10 hertz, they're about 400 kilometers apart. And then over the next 10 or so minutes and about 10,000 cycles, they get together and before they merge. Mostly this stage is essentially, if you want to study neutron star matter, there isn't much of an imprint. So it's typically what we call the point particle stage, where the neutron stars effectively act as if they were black holes. if you took the binary and replaced one of the neutron stars with a black hole of the same mass, the signal would basically be identical. Now, there's some small subtleties here in this statement, like you have to not expect any kind of resonant effects, hit any resonance in neutron star modes, anything like that. But typically, we don't expect anything too dramatic to happen. And the signal in this stage looks like what you would have from two black holes. That doesn't mean that this stage is not very interesting, because that's how you measure neutron star masses. It's basically from these thousands of cycles that you observe when the neutron stars are slowly spiraling around each other, that you measure the masses. Here is the mass measurement for GW170817, the first neutron star binary, M1 and M2, the two masses in the binary. And I'm showing the measurement in blue and red for two different assumptions about the spins of neutron stars. The different assumptions are listed here in terms of the dimensionless spin. If you don't like dimensionless spin, this is the conversion to milliseconds. So a 1 millisecond pulsar would have a spin of about 0.4, depending a little bit on the equation of state, but rough estimate. Okay, so these are the masses of these objects. You see some pretty obvious things. For example, we can measure extremely well a combination of masses called chirp mass. It actually you can measure so well that it looks like the two-dimensional measurement looks like a one-dimensional measurement, looks like a straight line. We don't measure as well the other direction. So this banana extends quite a lot. This is because we can't measure the mass ratio of the binary extremely well.
Can I interrupt just a second?
Sure.
You have the formula for Xi in terms of the characteristic time for the spin. But then you have Xi is less than 0.89. If you put 0.89 in there, you get a spin period is really short.
Yeah.
But probably shorter than is physically possible.
Yeah.
So why do they use that constraint? One side is not talking to the other.
Yeah. So the breakup spin is probably around 0.7 depending on the equation of state. The reason for the 0.89 is because and I'll discuss this a little bit, from the gravitational wave side, there is no proof that this was a neutron star binary. And if you factor in, of course, there was an electromagnetic counterpart, still there is no proof that it wasn't a neutron star black hole. So the 0.89 comes from not wanting to assume that's a neutron star binary, because you see it makes such a big difference. So if instead of 0.89 you had 0.7, it would probably, this red would go up here. So it has a big effect. That's sort of what the last point I wanted to bring up, that your assumptions about the spin really matter. So if you're willing to assume these are neutron stars and they have low spins like you'd expect from the galaxy, it kind of changes the constraints.
Thank you, that's very clarifying.
So 0.89, that's from X-ray binaries?
The 0.89? No, the 0.89 is a technical limitation of the analysis. It does not have any physical origin. We used 0.89 for some black hole analysis as well, because that was a technical limitation of the model to use to do the analysis.
Sorry, and this T in this formula for chi, that would be the spin period of the merged neutron star.
No, if you have just one neutron star on its well, any neutron star there on its own, if it has orbital, like a spin period of 1 millisecond, it would have a dimensional spin of 0.4, so a single neutron star.
But so the merged object would have this spin period if it doesn't collapse into the black hole immediately.
No, so these are the spins of the pre-merger objects.
Oh, pre-merger.
Refer to the spins of the pre-merger
Oh, I
objects.
see.
Yeah. Okay, so as we've already started discussing, this is one of the points I want to emphasize. There are a lot of subtleties and uncertainties here, even when you want to measure the masses. But at least for this case, when all is said and done, it's really hard to deny the fact this is very consistent with galactic neutron star binaries. The masses are around here, 1.4, 1.3, 1.4, 1.5, which agrees very well with galactic observations of neutron star binaries. Okay, moving on. Now we go to the latest spiral, where the two neutron stars are very close together. And that's where the nuclear physics and the equation of state starts mattering. To just get a little bit of intuition for why that happens, I'm going to show you two simulations. These are numerical simulations of neutron stars merging that are as identical as possible, same mass, same location, same velocity. I'm going to press go in a second. The only difference is the equation of state, and you can already see the size. These are big neutron stars or small neutron stars, and they're close together and they start orbiting around each other. And you already see the difference. The big ones evolve much faster. They are going to merge first. I'm going to merge in about a second. There you go. They're merging now. Well, the smaller neutron stars take longer to merge, and they're still happily orbiting about each other. Eventually, they will also merge. But kind of schematically, the first order, this is the effect we're trying to see. Big neutron stars lose their energy faster and merge faster, small neutron stars. This whole process takes longer. Instead, in terms of a little bit more mathy formulation, this is just your standard theory of tidal interactions. You have a spherical object, neutron stars are spherical. You put in an external tidal field, it will grow a quadrupole moment. In a binary, this happens twice. So you have one object creating a tidal field here, and that tidal field induces a quadrupole moment on the companion, and of course, vice versa. And the constant of proportionality in this equation is the tidal deformability. You might have heard this term before, for example, talking to Carolyn or Elias Moss was here. It's basically the main quantity we're interested. If that quantity is large, it means that the neutron star gets deformed a lot. If that quantity is small, it means the neutron star is not deformed as much. And that's a direct observable, because this kind of quadrupole deformation really affects your signal in two ways. The first is a quadrupole, it requires energy. And the only energy reservoir in the binary is the binding energy. So in order to make a quadrupole in your system, you have to remove some binding energy from the orbit. The second is, as you know, gravitational waves are sourced by quadrupole moments, by changing quadrupole moments. The dominant quadrupole moment in the binary is obviously the orbital motion, but this is another quadrupole in your binary. So that will create additional emission of energy. So it will accelerate the merger. Both of these effects basically accelerate the merger. If you plug in numbers, this ends up being about a factor of 2 to 3 stronger than this, but both of them operate at the same time. Remove energy from the system faster, which means that this is an observable outcome. If you want to plot the signal just to get an idea, these are gravitational wave signals as a function of time and as a function of frequency. Maybe the projector is cutting off a little bit all my references, so if you're actually interested in references, you ask me later. So let's look at the gravitational wave as a function of frequency. We're talking about high frequencies because we're at the late stage of the inspiral. And if you look at signals with the same neutron stars, just different tidal properties, 0 would be something like a black hole, 300 would be a more compact neutron star, 600 would be a bigger, less compact neutron star. If you follow with your eye sort of the peaks of the waveform, you see that it goes blue, pink, green. So the more compact you are, the longer it takes to lose energy, so the slower this process happens.
If the neutron star has its own high spin, then the shape should also be elongated, right?
Yeah, that's right.
So how strongly this effect will affect here?
Yeah. So if you calculate exactly how this phase goes, you have a spin-induced quadrupole and a tidally induced quadrupole. I'm talking about the tidally induced quadrupole. The spin-induced quadrupole comes in, and its effect is proportional to the spin, obviously. So if the spins are small, it will be a truly negligible effect. You need to have extremely large spins, like the 0.7 we're talking about, to have this be important. But the analysis does take it into account, just because we allow the spins to be large. The analysis does take it into account, but we don't expect it to be a very informative effect. Okay, so for GW170817, the first neutron star binary, here's what you get if you try to measure the tidal parameters. Here is lambda1, lambda2, the tidal parameters of the two objects, computed with different analysis, different kind of methodologies. I'm not going to go into detail for how each one comes about, but you have results here, the orange, blue, and green. There's slightly quantitative differences, but qualitatively the picture to get out of this, this system is that we are ruling out bigger neutron star. So in the upper right corner of this plot will be the less compact neutron star, where the tile deformation is large, so the objects are large. Well, down here is where the object will be small, tile deformation is small, and it looks like the measurement is concentrating down here. So the big sort of conclusion from gravitational waves is that they would put an upper limit on how big neutron stars can be. If you want to do the calculation, it ends up being about 13 and a half, your upper limit. Remember my plot from the beginning with equations of state, there were candidates that would predict neutron star radii up to 15, 16 kilometers. Those don't seem to agree with the gravitational wave data because we have an upper limit of about 13 kilometers.
Very simple question. So here you are using the word compact. So this is what lambda and r. They are in analysis they are correlated in some way, or they are analyzed separately, but they both have effect.
Yeah. So the gravitational wave signal only cares about lambda. This is the parameter we measure. So you can basically do an analysis like this without making any assumptions about the radius. You can just get the signal. It only depends on lambda, nothing else. If you want to go one step further and link this to, for example, other radii measurements or get a number like this, that's when you have to start making some assumptions to how to link this to this. And I'm going to get into this in a second, but there are ways under some assumptions, assuming normal-ish equation of state, which means no phase transitions, just hadronic matter, to go from this number to this number. They're not it's not a one-to-one mapping, but they are related. Under some assumptions that nuclear physicists have been litigating forever, and we always have to be careful. But you can get this number without any assumptions. Okay, there was another interesting binary. I don't want to say neutron star binary because it's one of the points that we don't really know, that we sometimes forget, but it happened. 1904-25 was also a very low mass binary. That was very interesting for the following reason. So if you look at the total mass of neutron star binaries, we have something like 20 or so neutron star binaries in the galaxy, and their masses seem to be concentrated very tightly about 1.3, 1.4 solar masses, which means that the total mass is about 2.7, plus minus a little bit, but it's about 2.7. GW170817 fell squarely in there. It's the poster child. It looks exactly like you would expect from the galaxy, but this new guy does not. It's very different from galactic neutron star binaries. This is GW1904-25. Orange and blue is again what you would get under different spin assumptions. Now, this really doesn't look like any neutron star binary you've seen before. So we really don't know what kind of spin assumptions to make about this. If you want to quantify exactly how, the difference here is about 5 sigma. It's about 5 sigma heavier than other neutron star binaries we've observed. Now, it's not an outlier in terms of neutron star masses. It's an outlier in terms of neutron star binary masses. What I mean here, so the mass is about 3.2, 3.3, which means about 1.7 plus 1.7, something like that. 1.7 is a very typical neutron star. We've seen neutron stars up to 2 solar masses or so. But those neutron stars are never in a binary around another neutron star. They're in a binary typically around a white dwarf. So we've seen neutron stars like this before. We've just never seen a neutron star binary like this before. Oh, that was that side. Okay, so the good news then is that we finally know that those massive neutron stars that we knew existed, now we also know that they form binaries and merge, if you are willing to accept this as a neutron star. The bad news is that it's next to impossible to measure anything related to nuclear physics and tidal interactions because those are intrinsically weaker. This statement has nothing to do with equation of state in nuclear physics. It's kind of a very simple physics statement. A big object, a more compact object, a more massive, more compact object is harder to deform. So intrinsically, the effect you're trying to measure is weaker, so it is harder to measure it. So if you, it's okay. So if you try to do this measurement, on the x-axis here will be the tidal interaction, the tidal deformability parameter I measured that's slightly cut off. If you try to measure it for GW19 of 425, you'll see that we place an upper limit somewhere about here, but the physically interesting region is down here. This is where, if you have a binary of this mass, you would expect tidal interactions to be down here. Our upper limit is here, so that's not a competitive measurement. And that will continue being the case for a long time, including potentially into the region of next generation most advanced detectors, ground-based detectors, we can see. These very massive objects, these very compact objects, they don't tidally interact with each other, so it's extremely difficult to actually differentiate them from black holes. And if an object at 1.7 solar masses, you're happy to call it a neutron star, even though there's no proof from the data, hold that thought, because I'm going to push the mass even higher to regions where we might be uncomfortable making any assumptions like this.
Is there a simple reason why the total mass of the binary neutron stars is lower, not 3 point something?
Lower than
why
what?
Massive neutron star tend to pair with another white dwarf, but very rarely pair with another.
So the reason for this, no, actually it is not known. There's a lot of, after this discovery, there was a lot of discussion, and they're still ongoing. Maybe there's an observational selection bias. If you have more massive neutron star binaries in the galaxy, maybe they merge faster and you don't see them, or they're radio quiet, so you don't see them. They lose when they fill it, something like that. It could be an observational selection effect. It could be something that they're not made. It's an open question. Or this might be a 1.7 from mass black hole. We don't really know.
The LIGO detection volume would be almost the same, right, for 2.7 and 3.3 total mass.
They're not the same, but you can correct for it. Yeah, similar.
Tens of percent, maybe.
It goes as mass to mass cube, so it's, yeah. Something like that. Okay, so I'm gonna,
Because the mass ratio is very poorly constrained.
yeah, they're all consistent with one, also consistent with a third, so.
Are there other knobs you can turn? Like how solid is the lower limit? For example, can the spin misalign or something? Is that can I change this?
This lower limit?
Yes.
Yeah,
how
it's
solid
very.
Is there other things you can change? Like do you assume the spin are aligned? Like
Yeah, but the spin assumptions only affect what happens on the upper side. See, between the orange and the blue? The spins won't push. This lower limit actually comes from the measurement of the chirp mass, which is so robust, so well done. It puts a sharp lower limit here. Other assumptions can affect the upper side.
How does the plot look if you were to do it as a function of chirp mass? I mean, the GW thing will be very narrow. Is there a good chirp mass measurement for the galactic? Do you know the mass ratio also?
Yeah, for some of them, you can plot them here.
Is the discrepancy bigger? I mean, it's measured very well.
No, it's about the same order of magnitude. Yeah, so you can get you get the same kind of, because we measured mass ratios so poorly that it's not much of a difference.
Yeah, that's why I'm saying the GW would have a chirp mass, which would be a delta function.
Right.
But maybe the galactic binary interests also have good, well-determined mass ratios.
Not as good. Well, not good like the gravitational wave, but still, this separation does exist. You only plot in chart
Some of
mass.
them, you know, masses exactly, so you can
Yeah.
determine that.
Right, some, but not all of them. Right, I think that was the question. That maybe for some of them, they could have higher chart masses and reach that.
I was just wondering, I thought that maybe the separation would be more clear.
No, you still have a clear separation
Yeah.
in terms of chart mass.
Well, it would be useful to see this versus chirp max.
There is, so this plot comes from the LIGO Virgo paper that first announced this. There's another paper led by Isabel Romero Shaw from Monash, where she plots in terms of chirp mass. That's why I'm saying that I've seen this plot and there's a separation. So there is this plot in the literature.
I believe it, I just thought it might be
Yeah.
interesting, but that's what people are referring to.
Okay. It's always a struggle to decide whether to plot things in terms of the niche quantities that we like or the quantities that all other astronomers like. Okay, who cares about chirp mass if it wasn't for gravitational waves? Okay, so let's see. I'm gonna skip a couple of things because you have a lot of great questions. So I'm gonna then jump to actually equation of state constraint, which is what I said the kind of big overarching question I started with. So this is what happens when you fold a bunch of measurements together. So this is the emerging picture about mass and radius. If you remember when I started this presentation, I showed you a version of this plot with nuclear models ranging from 9-10 kilometers up to 16. Now this is a plot with actual data and constraints. So there's a lot going on here, but what happens is if you take two lines with the same color, so for example, these two green lines, they enclose 90% of the probability. So these are basically posteriors, and the lines show 90% credible intervals. And the different colored lines show what happens when you take into account different data. The black is the prior, so what you start with no data, a large extent down to 8 up to 15, 16 kilometers, and then you start adding data. The first thing we know about neutron stars from radio data is they reach masses of about 2 solar mass. This is a very big constraint. It tells you that whatever the properties of matter inside neutron stars, the pressure must be high enough to support 2 solar masses worth of matter down to a ball of 10, 12 kilometers in radius. But the pressure is high, which means that the radius is high. So at least the radius cannot be too small. So that pushes you from the black to the light blue. It pushes the radius up to slightly higher values. The gravitational waves have the opposite side. So it's the opposite effect. They push you from the opposite side. Remember I said we have an upper limit on the radius. So it pushes you down from the light blue to the green and puts an upper limit on the radius. And recent, nicer X-ray constraints have the opposite effect of gravitational waves. They actually push you up to slightly higher radii. That would be, you go from the green to the dark blue. So that's sort of the picture emerging from these data sets. You have a radius of about 12 and a half kilometers, certainly about 1 kilometer. But the good news from this is that you actually have constraints pushing you from different directions, which is the best case scenario.
I don't understand how the pulsar data pushes you as a function of mass. I mean, it gives you an upper limit on the mass, right? So, but I mean, how does it?
Can I answer the question in the next slide?
Sure.
For the upper left, like it seems like black holes are like really pushing the prior even. The blue contour is like even to the left of the prior.
Yeah, but I mean,
So
this is
the green
90%, so it's not like a sharp limit. So this have extent. So if you take the rest 10% of the probability.
It strongly favors, GW strongly favors upper left. I mean, if you're pushing
Yeah,
the prior beyond.
It wants to come as much in this direction as possible. So to get to the question a little bit, to your question, I'm going to show you the same thing in pressure density, the same constraints in pressure density to see what happens. So you have the prior in black, and then you start adding data. So the heavy masses we're talking about need to increase the pressure. So they take you from this to this, from the black to the light blue. And that affects basically a lot of densities. Mostly affects what happens in the higher densities, around 5-6 times nuclear saturation, but it also affects what happens in the outer layers. The neutron star is not, the equation of state is not completely independent from density. You still need to satisfy things like stability, that needs to be increasing. With pressure, energy density, it needs to be increasing.
Okay, so
and you need to have, you need to satisfy causality. So the pressure cannot increase too fast. So if you want the pressure to be that high in there, it can't be too low here, otherwise you'll exceed the speed of light.
you're saying that, if you go to the previous plot, that if you drew the mass radius diagrams, it's the ones which have sort of saturated the mass of around 2 solar masses that, if you continue them to the lower masses, they would exclude this region at small radii, is that? So it has nothing to do, effect, I mean, well, if my neutron star has a mass of 1.4, then I don't think from pulsar data we can set any constraints on its radius.
If you plot typically equations of state, very roughly, it kind of look like this.
Yeah.
Very roughly. This is why this line, the black line, has this structure. So if you put a limit here, you're gonna rule out a number of things down here.
That's what I'm effectively
Yeah.
saying. But I mean, along this line, you can choose any mass, right?
Along this line? Or-
Well, no, along any of these curves, you can choose any mass.
That's right.
So what about the curves which you have just excluded? But I'm just putting a lower mass than this upper limit.
Yeah, so this line
Oh, you're saying, okay.
would
I
be
mean,
inconsistent.
Yeah, so
Maybe we can discuss it
for
more.
unique equation of state, right, okay, that's fine.
Yeah, so this line is ruled out because it can reach this mass.
We're gonna talk about the nicer data.
Sorry?
We're gonna talk about the nicer data explicitly.
This is the blue here.
Nicer data.
That's the next date is the dark blue, right? It's this. And I'm gonna show it in the next plot as well in terms of pressure. What happens is, the maximum mass pushes you up, and then the gravitational waves decrease the pressure because
My point, I'm sorry to interrupt, because again, back to this Roman's question, I think the nicer data constrains M over R because of the timing effects of GR and the bending of the geodesics.
it depends on the rotation speed, but yeah.
There is an R constraint specifically for a given mass.
Oh, yes.
So
Yes.
so it's not merely from the causality arguments or anything like that.
Right, so this is just the maximum mass. This is the gravitational wave, and this indeed comes from NICER, which is a direct radius constraint. You're right.
That's why Roman asked this question.
Okay.
So, thank you. Speaking for him. So,
Okay. So then the same kind of constraints in pressure density I just described, that radio pushes to higher masses, gravitational waves push to higher pressure. Gravitational waves push to lower radii, which translates to lower pressure, and NICER, the X-ray data, push to larger radii, which means the pressure push the. So again, the good news here is that you have constraints pushing from different sides. Another thing you might think is good news, and actually it is good news, you also have constraints at different densities. I very intentionally picked the x-axis location of those vectors to show more or less what densities the different data are informative about. So the maximum mass is mostly informative about what happens at the central layers of the star. So if you think about it, mass is typically concentrated at the center in the star. So what determines the value of the maximum possible mass is the conditions at the center. On the other hand, if you have radius measurements from NICER or tides measurement from gravitational waves, those mostly care about the conditions in the outer layers because most volume is accumulated in the outer layers. So the radius is determined by the conditions and the properties of the star in the outer layers. So this is why those constraints are down to maybe 2 times nuclear saturation. And while not included in this plot, if you want to look at nuclear theory for calculations or even nuclear experiment, those would be even lower densities. So something like theoretical calculations or experiments would be mostly informative about what happens at even lower densities. And I should mention, there are also some calculations for much higher densities as well. But this picture is that you have constraints and calculations informing you about different densities inside the neutron stars, which is great because you can actually get more information this way. However, there's a little bit of a problem here if you're if you want to be super careful, because when you have constraints about different things, if you want to combine them, you need to have some way of translating, for example, the conditions at 2 times saturation to the conditions at 6 times saturation so that you can combine the measurements. And typically we do this with a model for the equation of state. So we draw lines for pressure density, lines like this, example lines like this, and then compare the data to those lines. So whatever constraint you have at the end will depend on how good the lines you draw are and how they're, so to some extent they're going to be model dependent. So to show an example of how this could be, and the problems with this, here's an example plot of different models. So this is again the same pressure density plot obtained with the same data, but with different models for how to write down equations of state. The blue here is a non-parametric Gaussian process model, so it's the one that has the most flexibility. And the others are analytic models. You might have heard the names if you work on neutron stars, like spectral decomposition, piecewise polytropes, and a speed of sound parameterization. And which you use, of course, has a big impact. Say you introduce a very strong constraint in one density. If you only want to be informed by the data, something like this should happen, right? You pinch in that density and then you don't get much effects in other densities. Effect should not propagate in other densities you don't have data for.
But you're emphasizing now, these are the nuclear physics constraints and experimental constraints. In the previous slide, you had a very wide range that was only astrophysical.
No, these are astrophysical constraints. But I'm putting in an example. Say you had a really good measurement of the pressure in one density.
We do.
Right, so this is sort of an example that I'm showing what happens here.
That's the nuclear physics, but in the previous slide, you didn't include that.
Right, I'm using this as an example.
You're leading up to something.
Yeah, so if you have a very good constraint here, ideally you'd like your result to only incorporate that constraint and nothing else. So that would be a kind of more flexible model.
But I think even your mass radius plot includes physics, because you are assuming certain runs of these mass radius relations from the nuclear physics models to exclude them. I mean,
these are example models I draw. It's not exactly what the blue uses. The blue uses draws from a Gaussian process that don't include that kind of information. But as a schematic, this is what they would look like, the ones on the right.
A lot of those equations of state we saw in the beginning do not fit the nuclear systematics of nuclear densities.
how are they moved up?
But
How are they moved up?
they're historical. They might have fit at one time.
Yeah, a lot of them are ruled out.
Yeah, a number of them are already ruled out.
Just as an example of what
But for
people have done.
completeness, you generally include all these. Perhaps there should be a color
So
code.
they are not based on microphysics of, or.
They were at one time, yeah.
At one time, but then.
Sorry to interrupt.
But the point is that you kind of have situations where your data are informative about, say, what happens only here. But because of the models you're using, you might end up with constraints at other densities, like here. This would be the red arrows. So this is a concern for someone like me who's interested in making sure that we get good constraints in the equation of state, that we need to be careful about the kind of models we are using to actually compare the data that come from different densities. If we have constraining models that can introduce correlations between the different densities, that might make us think we have a constraint here, but that constraint comes from just the model, doesn't come from data, for example.
So what are the assumptions of the 3 others?
So the 3 others are analytical. So this comes from a Gaussian process. The other 3 are analytical. They make use of a small number of parameters.
Okay.
This, I can go into more detail maybe later, but basically this is a collection of polytropes. This is an expansion of the pressure in terms of logarithms. And this is interpolation of the speed of sound. But I can go into more detail about the exact analytical form.
Okay. Let's start. Even if for the Gaussian process model, right, you assume some correlation, like smoothness of the curve, right?
Yes.
So it's not really assuming nothing.
Yeah.
It's
So-
these 4. It's basically about picking what you want to assume. It's not that one is so free that it assumes.
Yeah, so I can go into more detail, but this is actually no construction pressure density, so it can be It can actually lead to discontinuities, for example, in mass radius and multiple branches. And it probes a large range of possible correlations. It's a combination of many Gaussian processes. I can go into detail about the math and the kernels used if you're interested. But this can, for example, reproduce something like phase transitions and discontinuities. Okay, let's see. I have 10 more minutes, so let's see. Skip a couple of things. I want to discuss a little bit neutron star black hole binaries. Because this brings us back to the question of, if you have a very heavy object, are you comfortable calling it a neutron star or a black hole? That's the point I want to finish with. Which brings us, of course, neutron star black holes. So neutron star black hole binaries have been now detected with gravitational waves, and the gravitational wave signal roughly could be split into two categories. And the two categories are the red and the blue here. If you have a situation where the neutron star just falls into the black hole, this is a kind of a still from a simulation where you see a neutron star in blue crossing the apparent horizon of a black hole. The signal looks very much like what you would expect from two black holes. That would be the blue signal. While on the opposite extreme, you can have, as the neutron star is approaching the black hole, it could be completely torn apart, completely disrupted. So now the signal kind of shuts off because you no longer have two compact cores orbiting around each other, so there's no signal. And that's again from a simulation where the neutron star is completely torn apart around the black hole.
So what is the difference in radii? I mean, you blocked it off.
Yeah. It's this.
So the first is a black hole like, and the red one is
Yeah, this black hole like is very compact. The black hole tidal field cannot disrupt it, it falls in. So basically it's a tug of war between those two effects, right? Does it fall in or does it get disrupted? And the more compact it is, the more this is going to win compared to this. Now, this picture is nice and intuitive. In reality, for most of the parameter space, unfortunately, this is what's going to happen. Which means that if those things plunge immediately into black holes, it would be hard to actually get any tidal imprints, to get any signature of the neutron star itself. The signal looks very much like what happens when you have two black holes merging. Sometimes this is a problem, sometimes it's not a problem, depending on how risky you want to be with your assumptions. So here are the observations. M1 is the mass of the heavier object, M2 is the mass of the lighter object. The heavier object, we're talking about 5, 10, 20 solar masses. These are black holes, right? The lighter objects have, well, very uncertain, but typically 1.5, 1.7, maybe 2 solar masses. There's no proof that these are neutron stars, but maybe you're willing to assume they're neutron stars. This is what happens, for example, with 1904-25 I mentioned earlier. You might be willing to assume it's a neutron star. Maybe that's not a problem. The situation is a lot more dicey with something like this. This is a 2.6 solar mass object. And that, from the gravitational wave signal, there's no information about whether this is a black hole or a neutron star. It's so compact that gravitationally, it behaves the same, whether it's a black hole or a neutron star. We will never learn what that object is from gravitational waves, even when you have third generation detectors. It's so massive, there's no tidal signature. So what do? Is this the lowest mass black hole ever observed or the highest neutron star mass ever observed? Either of these is interesting, we just don't know which is which.
So which event is that? 1904.
This is 1908-14. It's it should be this one. Yeah. Okay. So at this stage, when you don't really, the gravitational wave data will never tell you the answer to this, even with the best next generation detectors. So you need to get some kind of external information from other people interested in neutron stars. Nuclear physics kind of predicts what the maximum mass could be. That gives you the green line here for how big neutron stars can get. So if you want to trust that information coming from equation of state, maybe you can say 2.6, it's on the high side. there's more information about neutron star masses coming from galactic observations. This would be the dark green here. That we've seen neutron stars up to 2 solar masses, but not above that. Well, not confirmed above that. There are some candidates at higher masses, but there is a little bit of uncertainty. So if you're actually willing to say they only come above 2 solar masses, and there's a reason we don't see anything above 2 solar masses, maybe they don't exist above 2 solar masses. But all these arguments are necessary if you want to interpret this kind of object. But as I'm describing those kind of additional pieces of information, I keep saying how uncertain they are. They depend on what assumptions you're making about the equation of state. They depend on how you want to actually treat the neutron star observations. They depend on whether you want to assume that the galactic neutron stars are actually representative of LIGO's neutron stars. I just show you an example where they're not. I don't have time to discuss this into detail, but I just briefly want to show you this plot, which is neutron star masses. In the neutron star binaries in the galaxy are the dot dashed, they concentrate around 1.4. This is the result we were discussing about half an hour ago. All neutron stars in the galaxy is the black. They really like 1.3, but there are things up to 2. And the gravitational wave neutron stars don't look like this. They are either the orange or the blue, depending on what assumptions you want to make. However, no matter what assumptions you're trying to make, it's pretty clear there's no sharp kind of peak here. In the galaxy,
How many binary neutron stars you have in the LIGO?
this includes 6.
Some of
4 in binaries and 4 in neutron star binaries and 2 in neutron star local binaries.
But what are you doing about the 2 point something?
This is not included here. So if you look at the things that are below 2 solar masses and look at their mass distribution, the question is there a sharp peak here like you see in the galaxy? And there is no sharp peak here. You kind of get the same number here as here. And that folds in things like selection effect, observational issues, uncertainties, et cetera, et cetera. So we know that what you see in the galaxy is not the same as what you see in gravitational waves. So how willing are you to actually lean into that information from the galaxy to interpret the object that's out here? Are you willing to stop here and say that this cannot be a neutron star? Are you not willing to make that assumption, et cetera?
There's this small correction, well, not completely small correction due to rotation of neutrons. The maximum mass goes up by 20.
Yeah, so you can get that 2.6 down to a little bit like 2.4, 2.3. But then you have to figure out how that neutron star managed to be spinning that rapidly, that late in the evolution of the neutron star black hole. So there, the point I want to leave you with is that I don't have any answers to this. There's a good chance gravitational waves cannot tell you the answer to this ever. They're inherently difficult measurements. And we need a lot of external information from nuclear physics and astrophysics to try to understand all these uncertainties.
Sorry, how many binary neutron stars are observed in the galaxy?
It's about 20. And the subset of these will merge within a Hubble time. I don't remember how many. It's about 20. Sorry, neutron star binaries, you said?
Yes.
This one? Yeah, it's about 20.
Galactic, but
It's about 20. Yeah.
Okay.
You remember?
Neutron star binary.
Yeah.
They're neutron star white dwarf binaries are about 50.
Oh, yeah.
Okay.
These with so this is everything with the mass measurement, the black line. And that includes neutron star binaries and neutron star white dwarf binaries. And this is tens of objects. Yeah.
Like for the population models, like using very metallicity or something like that, to those models, like I guess there are enough knobs so you can reproduce this population models.
Which one?
The LIGO curves, are they like well modeled, or is it like a?
The problem with population models and neutron stars is not so much the mass. You can get the mass. You can have a wide range of possible masses if you factor in supernova physics. The problem is getting the rates of neutron star binaries. It's very difficult to get how many we're observing. Clusters cannot do it because they're too low mass. The question is how many of these you can make in the field. Numbers are lower than what we're observing, but That's sort of the big uncertainty, the population model.
Population synthesis approach is rather crude. And their model of supernova is wrong. Whatever's right, it's wrong.
This red and blue curves, I mean, they're based on how many neutron stars, I mean, in gravitational waves,
6.
which are black hole neutron stars.
Oh, 2.
2.
4 from binaries, so 2 plus 2 from the 2 binaries. Plus we have 2 neutron star black hole binaries, so another 2 neutron stars.
That's amazing in itself. We don't have any of the galaxies.
Neutron star black hole? Yeah, isn't it?
That's been an embarrassment for a while.
I'm not gonna say
Right, so
that. for sure.
that by itself might add another, peak at higher masses or something.
Which can add a peak at higher masses?
Potentially, a peak to the neutron stars. I mean, we just don't see any black hole neutron stars in the galaxy, so
Yeah.
who knows? I mean, there may be a peak there. I would probably expect.
But still, even if you consider the binary neutron stars, one is here and one is here. If there was such a huge abundance of systems here, we wouldn't have seen 1 plus 1. We would have seen a lot more
No, talking
here.
about the ones in black hole neutron stars, with a neutron star with a mass of 1.8 or something.
Yeah. Yeah, those,
They are completely hidden. They are totally agnostic about their existence.
that's right, that's right. I'm saying that the lack of peak in the blue and the orange would be here if you also exclude the neutron star black holes. If you only had the binary neutron star signals, there's one here and one here.
Yeah.
So no large peak here.
Yeah.
Alright, but the peak is a factor of a few, like you have 2 examples, how unlikely is it that one is in the, I don't know.
It's a log scale, it's about a factor of
I'm
10.
not saying just a factor of 2, I don't know. 3, so factor of 3, and you have 2 examples, probably it's possible, I don't know. How unlikely.
Yeah, so those uncertainties take that into account. So the orange band,
One of them is with just the 2. One of those curves is with just the 2.
no, all of them have 6 neutron
Yeah,
stars.
exactly. I was just saying that if you did the exercise with just the binary neutron stars, probably the thing would be much broader.
Oh, yeah, absolutely. I mean, if you have 6 objects and take 4 out, the 2 remaining ones are not going to be very constrained. That's right.
Fine.
Yeah. So I'm going to skip a couple of things because we're already past. Actually, I don't know how to fix it. Okay. I actually wanted to finish.
Another cool thing.
Yeah. I just want to say a little bit about next steps because we are a little bit past noon. Just to say this is the observing schedule as a function of time. I guess we're further than here. We're kind of second half of 2023, but we have the first 3 observing runs. The 4th observing run started in May, only with LIGO so far. And there are no neutron star binaries, but the estimate is to expect something like order 10. I would probably, let me remove this, sorry. The estimates before the run would expect something like 10, but those assumed a slightly better sensitivity than the detectors currently have. In reality, I would probably expect that to be lower, and so far there's 0, so there's some math to be done there. But there's 2 neutron star black hole candidates that have been announced. Because we're discussing this with Jay, I really want to mention, if you've seen neutron star binary announcements like going by, those were retracted. I'm talking about unretracted things that we still think are candidates. There are no neutron star binaries in there, but there's 2 neutron star black hole binaries. All this, there's going to be a lot more data in the next few years. There's all sorts of excitement about gravitational waves at the same time. You had a discussion about NICER also using neutron stars for gravitational waves with a completely different spin. And next generation detectors coming after this. So we are currently in 04, and there's going to be plans for 05 and going detectors even further than this, up to 3rd generation detectors that are about a factor of 10 more sensitive than the current detectors. So just want to finish with a bit of a summary. We're mostly putting upper limits on tides and radius. But the constraints we're getting from the neutron star masses and from neutron star tides are interesting, and we are actively discussing comparing them to other information from nuclear physics and astrophysics. And I'll end here. Thank you.
There's a severe selection bias in determining the mass distribution, for example, of black holes. The number of these sorts of systems. So what attempt is there to correct for that?
Yeah, any plot.
Underlying statistics in a given volume.
Almost any plot you've seen about black hole mass distribution has corrected for this. We see something like, you see the mass plots of the mass distribution. Kind of look like this, where this is about 10 and this is about 30. These plots always correct for the selection effects. The way to figure out if they have is, in reality, we are seeing about 3 times as many of these than these. So if actually somebody's plotted without the correction, it would look like this. It's a big effect, and it's almost always corrected because it's such a massive effect.
I'm glad you're seeing the lower mass.
Yeah, so are we. They're a pain to analyze, but so are we. They're long.
Not sure really that the equation of state curves, that equation of state is actually a unique thing for all neutron stars. I mean, could there be some hysteresis effects in the formation process where, you know, have entropy, you have neutrino effects and so on? I mean, like, can you jump on one curve or be on another curve? Like, you know, for example, you know, coming back to this upper, you know, Pulsar constraint of 2 solar masses, could it be that, you know, there are some neutron stars are on one equation of state that allows them to reach this regime of heavy massive neutron stars, and there is another branch of equation of state that allows, you know, maybe low mass ones.
Yeah. So
Smaller radii.
I'm not sure about anything. It is possible. The canonical assumption is that lowest energy state, everything follows the same equation of state. So everything in pressure density falls on one curve, or pressure energy density falls on one curve, and that gives you some mass radius curve. Now, it is possible to have very different scenarios. So maybe some objects, there are ideas about quark stars that are also as compact as neutron stars. So you could think they're neutron stars if you just measure mass radius, but there could be a second population of them. But I don't know if that's what you're asking about, but you're still thinking of neutron stars. I mean, it is possible, but from everything I've sort of read, nuclear physicists are thinking this is unlikely, but it is possible, obviously. Those are very old, cold neutron stars. So things like temperature effects are not going to be a problem until they merge,
right? Obviously.
But if something happens during the formation that they end up in a different, you know, energy minimum, then you could have a situation like this. Yeah. But typically we assume it's the same equation of state, which doesn't mean the same mass radius branch, right? It means just the same equation of state, same pressure density.
Well, I mean, if you solve Oppenheimer-Wolf equation, this same equation of state, you get the same branch, right?
No, if you have a phase transition, you might end up with like disconnected branches in mass radius.
Okay.
So one neutron star hasn't undergone a phase transition, the other has. Those neutron stars could fall in different mass radius branches, but they would still have the same pressure density relation. The densities that are common in the 2 neutron stars will be described by the same equation of state. It's just that one neutron star goes to higher densities and there's a phase transition there. So things could look observationally very different, but when there is overlapping densities, the neutron stars have the same physics. That's the question. At the same density, could you have different physics?
Okay, thanks.
In the interest of time, let's thank Katerina.
Thank you.